All right. We are ready. Okay, so we have a few things to do today. Just gonna go get Moodle open.
Hey, can I ask a question real quick?
Yes.
So you know how the deal with the midterm is we send it to you through email?
Yes.
I was wondering, by any chance, is it possible you can create a Moodle link where we can just upload it? Do you know what I mean?
Yeah, I've tried that before and it didn't work. And
Oh,
technology isn't my thing. And I just thought, you know what,
no,
it would
it's
just be
no
so
problem.
much easier. If I really was a technology whiz, of course, I would do that. But, when I get a hold of the school and I ask them for their advice about these things, they don't always help me very much. So I figure, you know what, well, let's just keep this going. It's just less aggravating. Let's put it that way. Because yeah, I mean, I've tried and it just didn't work.
I totally
So,
understand.
you know,
One other thing, is it possible? It's like we're very close to finals now.
yes, we are.
Is it possible if you can just upload the sample final now so
Oh,
we have more time to practice?
is it not there yet? Okay. Oh,
I
all right.
I didn't
No,
look
you're
yet,
right.
but I wouldn't even know. But I'm just asking just in case. That's all. But it's just I'd rather have more time to practice now than
Right. Yeah.
have just a week to practice for finals and just have 2 hours to do it. You know what
Sure.
I mean?
Well, the thing is, we're going to go over it next week anyway, so I would have put it up probably today, but I'll make sure that I do it sooner
Thank
rather
you. I
than
appreciate it.
um, the thing is, I just wanted to double check it and make sure because every semester is a little different. The thing is, some years we cover more materials than other. It depends on a lot of things like when we're in person, for example, sometimes the weather would cause problems and then we end up with slightly less material and sometimes we have slightly more. And so I just want to double check it one more time to make sure everything that's on there is what we've actually covered.
Gotcha.
And then I'll post it. It's only going to be an 11 and 12 anyway. So if it's not completely ready, it's like 95% ready. I just want to double check that all of the questions in there were things that we actually got to cover it. Because like I said, every semester is a little different as far as how far we get. So don't worry about because we will have to do that next week anyway. So I would have probably put it up there tonight anyway. Fernando.
Hi, good morning, Professor. I have a good question for the sample midterm for the final one. That one's only be covering for the last two chapters, or will it cover the rest of the chapters?
No. It's 11 and 12 only.
Oh, may I ask why is it a bit different? Because I know you were just saying it's a bit different from depending on the classes, but ask for it.
Yeah, because every semester, some semesters we go a little faster than others. It depends on a lot of circumstances. Like I said, I mean, when we do this in person, sometimes bad weather causes us to miss a class here and there. And some semesters it just seems to go faster than others. And also, I'm always constantly trying to refine the class a little bit to make it better. Sometimes I'll take things out, sometimes I'll add new things. So it's not always exactly the same from one semester to the next. So, I definitely made some adjustments this semester. So I just want to make sure that the sample final that I have already written exactly matches what we've been doing. So just I don't want to put it up there and suddenly discover that I left in some questions about something that we never went over because I took it out, which I do sometimes. Some topics are more important than others, and sometimes a topic proves to be more trouble than it's worth, and I just take it out and I replace it with something else.
All right,
So,
thank you, Professor.
yeah, it's not like some classes that I've taught at Purchase, I've done so many times that it's pretty much all set. This one, I'm still updating it every semester because I find things that might be more interesting or more useful, and I want to put them in there. But I have to adjust then all of the question sets and the exams in order to do that. So it won't be, if it gets, tonight or maybe tomorrow at the latest, it'll be up there. And so that way you'll have the whole week to get it ready for next Wednesday, which is, by the way, our last class. I just want to remind everyone The semester ends. Let's see, let's get a calendar out here. Now, see, again, this is the thing that makes it awkward to have a once a week class. You don't have that much flexibility with the schedule. So yes, the week of the 13th is the official finals week. So if we'd been doing this in person, we would have had our final on the 15th. So next Wednesday will be our last meeting. But all we need to do here, we have to do the chapter 11 problem sets, finish 12, do the chapter 12 problem set, and then the sample final. But we have 2 weeks to do that, today and the 8th. So we should have no problem finishing everything up. And then since we would normally have the exam on the 15th, I don't think the grades are actually due to the following Monday, but I'll double check that. So instead of having it due on the say 15th, I could probably give you even more time to get it done, but this we will figure out later on. But the official date is the 15th. Now, we're going to cover the sample final on the 8th. And when we're done with that, I'll post the actual final. So you'll have an absolute minimum of 1 week to get the final done, probably more like 10 days, depending on how far I can stretch it out. It's not going to be, I mean, it's not going to be any longer, let's say. It'll probably be even a little shorter than the other two. So, it should not be taking you anything like 7 to 10 days to get it done, but I know you'll have other finals as well to worry about. So I want you to have as much time as possible. You'll, as usual, have all your notes available to you and all of these slides. And so that should help a lot. So, and you can always send me emails with questions if you want to. So I don't anticipate it being a problem getting it done in a timely manner. So anyway, yes. So, and in fact, if anything, we may even be a little bit ahead of schedule. So there's no danger of running out of time. Let's put it that way. All right. Well, anyway, with that being said, so what I've done is I've downloaded the 2 chapter 11 problems. There's one for each section of the chapter that we went over. For example, part 2 is all probability theory, and part 1 over here is, oops, that's number 2 again. Hold on. There we go. Part 1 is right here. This is all about sequences. Okay, very good. So these are the sequence questions, and then we'll have our probability questions, and then we can dive back into 12. And with 12, we just started to look at some fundamentals of calculus. And I mentioned before that, obviously this is pre-calculus. The next step after this would normally be Calc 1, if you feel so inclined to take it. And if you do, well, you'll be introduced to a lot of new topics, of course. So we want to sort of bridge the gap between pre-calc and Calc 1 by introducing you to some very fundamental concepts that you'll see in Calc 1 anyway. And if you never take Calc 1, well, it gives you an opportunity to learn some important principles of math without having to actually take Calc 1. Now, depending on what you end up doing, when you graduate, what you end up working in, some of this stuff will prove to be very useful if you end up in certain areas, like in, let's say, business or any kind of business applications. You ideally should have some basic math skills because, most business disciplines are fairly quantitative, especially areas like finance and economics. They depend very heavily on this stuff. Other areas of business like marketing, maybe not so much. And then, of course, if you end up in the performing arts or something like that, like so many of the other students at SUNY Purchase, well, then you may never see this again. I mean, you never know. It's hard to say, but it's, like any other skill set that you learn, you never know when you might need it. Okay. It's like, I don't know, like imagine yourself learning how to read maps when you're very young, and one day when you're lost in the woods or something, suddenly you realize you need to know how to read a map. Well, of course, if you have Google Maps, maybe that's not such a big deal, but you never know where skills will come in handy. So the more, the better. Let's just put it that way. All right. Well, anyway, so let's get to these problems. And not that one, the first one. Now, I know it's been 2 weeks, so you might have started to forget some of this material, which is okay. We'll go over that right now. And so we start by reminding ourselves, first of all, let's revisit the idea of the arithmetic sequence. An arithmetic sequence is a sequence where there's a constant difference between the terms. In fact, I'll tell you what, why don't we open chapter 11 again? Just to do a quick review of what exactly do we mean by an arithmetic sequence. Hold on. So just a very quick reminder of what exactly this is all about. An arithmetic sequence simply means we have a list of numbers in a particular order where each of those elements or numbers is called a term. And the most important detail here is that there's a constant difference between each of the terms. So here, for example, obviously that difference is 1. But we also have many other possibilities, like in the second case here, the difference is 3. And then in the third case, it's -1. You can have negative differences. And also they can be fractions too. They don't have to be integers. All right, so then let's get back to the questions. Sorry. So we're going to do 3 things here. For each of these sequences, we're going to determine what are the first 5 terms. Then we're going to calculate the 12th term, and then we're going to add up the first 12 terms. Now, you might recall that we have formulas for calculating a particular term in a sequence, and we also have formulas that enable us to figure out the sum of the first n terms. So we're going to take advantage of those right now. All right, so for example, in this first case, we know that A1, the starting term, is 1. And the common difference between the terms is 6. So that means that we're going to start with 1 and just continuously add 6 to that. And, of course, then we're not going to list them all, of course, because there's an infinite number of them, but we can see what the sequence looks like. All right, so again, we started with a 1, and then we added a 6 as we moved along. And so they're asking us for the first 5 terms. 1, 2, 3, 4, 5. All right, whoops, one too many. All right, so part A just simply asks us for the first 5 terms. So literally all you have to do is list them by looking at the common difference between them. And then for the 12th term, we've got a couple of options. What we can do is just write them out. I mean, just keep going, which you can certainly do. There's no stopping you there. Is that 12? Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's it. All right. So the 12th term is 67. And but we also have a formula that you should be comfortable with. And what the formula tells us is that for any term n that we need, we can find it by starting with A1, the first term, and then we multiply that by n-1 times d, where n is the term that we're looking for. So here we'd be looking for A12. So A1 is 1, n is 12 because that's the term that we're looking for, and the common difference is 6. So we'll have 1 plus 11 times 6. And what do you know? It's exactly what we said. Okay. Now, as far as the sum is concerned, we do have an amazing formula for that. Okay, hold on one second. See, all my icons are hidden right now. I don't know what causes that. It's very annoying. I can see them down here. Oh, here we are. Jesus, why does it do that? So I'm going to use the equation editor for this because the formula is fairly messy. Okay, it's taking its sweet time. There it is. All right, so the formula for that sum is Sn, Sn subscript. And then you might recall we have n, this is in the chapter, of course, in the numerator n, a1, the first term, plus an, the nth term, all divided by 2. Okay, that's the general formula. So we'll use this for every one of these cases. You could, again, if you really wanted to, you could manually add these up. But I think that might be a mistake because it'll take forever and there's a very high probability of making mistakes somewhere along the way. So we may as well take advantage of this formula. And what would we get? Let's see. So S12, sum of the first 12 terms. N is 12. A1 we already know is 1. And we've already determined that A2 is 67. All right, so that leaves us with 12 times 68 over 2, which could be rewritten as 6 times 68, and that is equal to 408. And that's all there is to it. And if you're really nervous about your answer, again, you can take out your calculator and add up those first 12 terms, maybe as a double check, but I would use this formula in this case because 12 terms is a lot. And if you have to ask for the 100th term or something like that, then you certainly do not want to add them up. All right, so we're going to do this exact same procedure for all 4 of these cases. Okay, there's B. And so why don't we start by writing out the first 5 terms. Okay, no problems there. Now, they're going to ask us for the 12th term. And we can do it again in one of 2 ways. We can just carry on for a while. See, is that it? 1, 2, 3. See why this is such a nuisance? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. Okay. Or use the formula. So I think you're starting to see why we should probably always use the formula. Because it's just quicker. Okay, so this time though, we're starting with 10 and the common difference is 5. So we'll have 10 plus 11 times 5, or 10 plus 55, which of course is 65. Oh, before we go any further, let me save this for a second. Yes, we do not want to lose any of our work. I'm sure you've all lost work on your computer when something went horribly wrong, when the power went out or something. You know what I'm talking about. By the way, today's the first day of December. I forgot to mention that. How do you like that? That shows you how fast time is flying. I hope you've all gotten at least a head start on your Christmas shopping because This year, apparently, it's going to be more difficult than ever to get things sent to you because of the supply chain mess. So don't wait too long. Oh, you know what else? There's one more thing I wanted to mention. If you need another math course and you really don't want to take Calc 1, I believe the school will let you substitute or use statistics as your math elective. And the reason why I'm bringing that up is because I'm actually offering that during the winter break in an online format. So if you look at the schedule, you'll see that it's Math 1600, Statistics 1 is offered during the winter session. And so what that means is it's completely online. And, you know, you'd be, of course, very busy with it, but you could get three, I'm not sure if it's 3 or 4 credits, but you could get a math elective out of the way during the Christmas break. And, you know, it might make your scheduling a little bit easier going down, you know, in the future. So it's something to think about. And you've already had some exposure to statistics. Well, a little bit in this class. It's a very interesting field of study because it's meant to be applied to any area you could imagine. It's very, very useful. And unlike what we're doing here, you can do a lot of the work with a calculator or else in Microsoft Excel. So here you really have to have a specialized software package like Symbolab or something even more advanced than that. But when it comes to statistics, there are a lot of calculators are easily able to do a lot of those techniques, but also Microsoft Excel is set up to do a lot of them as well. So again, if you're looking for another math elective, there you go. And also, if you don't want to, you know, Christmas break is fun and all, but maybe you'd like to get something useful done as well. And that would be an opportunity to try that. Okay. So that's all I wanted to say about that. Just want to make sure you're aware of that. So let's carry on. Where do we leave? Oh, I know. We're still in the middle of this one. Yes, for B, the 12th term is 65. And so we're going to do the sum. And so this time the terms are 10 and 65. Okay, it's taking its sweet time. Here we go. 10 and 65. And that's going to leave us with 450. Beautiful. Now for the third one, what do we have? Uh-oh, negatives. We have to be careful with negatives. It's so easy to make mistakes with negatives. So what do we have? -9, -12, -15, -18, -21. Those are the first 5 terms. Now, next, we want the first 12 terms. Okay, so let's do this. Well, actually, yeah, technically, we're only asking for the 12th term. Yeah, there it is, 65. All right. So we've got the first 5. Okay, good. All right. Let me just add that in here. All right, now, the 12th term, again, we've got 2 options. We can simply carry on, just writing them out. Let's see, is that 12? 1, 2, 3, 4, 5, 6, 7, 8. Nope. 2 more. All right, that's your 12th term. And of course, we have the formula. A12, therefore equals -9 plus 12 minus 1 times -3, -9 plus 11 times -3, -9 minus 33, minus 42. Well, there you go. We should not be surprised to see that that worked correctly. All right, and then of course we still need the sum. Let's steal this formula. All right, so so you can see that here, the first term was -9. And then for the next term, the 12th term rather, was -42. So we're actually adding -42, which is the same thing as saying subtracting 42. So we have 12 times -51. And that is the same as 6 times -51, which means -306. Okay, so the sum of those 12 terms will be -306. And then we have one more case to look at. Okay. So now just with this one, of course, because of the negatives, you just have to be a little careful. Don't subtract when you're supposed to be adding and revert vice versa. All right, what about D? Let's see what D is. Okay. All right, D is, here we go. Oh, more negatives, wow. Okay, well, it could be worse. It could be negative fractions or something like that. That would really be bad. So the first 5 terms are -15, -17, -19, -21, and finally -23. And then when we go to look for the 12th term, we'll just carry on with this as one possibility. See, is that it? 1, 2, 3, 4, 5, 6, 7, 8. All right, and then of course we'll also try our formula. -15, and remember the difference here was -2. So we are left with -15 plus 11 times -2, -15 minus 22 is -37. And there we go. And then finally, the sum comes from our favorite formula. Okay, so let's plug in the numbers. So this time, the 2 terms that we need in the numerator are -15 and -37. Okay. So we're going to have 12 times -52 this time, or -312. All right, so that's pretty straightforward. So they're all the same. The only thing that changes is, of course, the values of A1 and D, but the techniques are never going to change. All right, good. So let's see what's next. All right, so it looks like what's coming up next, there's more practice coming up, except this time we have the actual sequence instead of A1 and D. Well, all right, that's no big deal. We can work with that. So you see what I mean here? For example, with A, they're giving us the actual term. So in other words, A1 is 5 and D is 8. You can tell it's 8 because we have a common difference of 8 to go from one term to the next, we keep adding 8. And so since we already know the first 5 terms, we don't need to do that again. But as far as 12 terms are concerned, we can do again one of two things. We can simply continue what we did here until we get to 12. See, is that it? 1, 2, 3, 4, 5, 6. That's it. So the 12th term is 93. But as usual, we can also do it with our handy formula. And so we started with 5, and the common difference was 8. So that should give us 5 plus 11 times 8, or 5 plus 88, or 93. Beautiful. And it just confirms that what we did is correct up here. All right. And then, of course, we're going to add up the first 12 terms as always. Let me just go grab those formulas real fast. Ooh, so they're going to spill over. Hold on. There we go. So you can see everything. Now, this time, n is still 12, but the 2 terms that we need are 5 and 93 in the numerator. 5 because that's A1, 93 because that's A12. And of course, this thing, here we go. So the first term was 5. The 12th term was 93. So we have 12 times 98 over 2, which is equivalent to 6 times 98, which is 684. Beautiful. All right. So they're all going to be the same once again. So by the time we're done here, we're going to be experts in sequences. That's for sure. So A1 here is 2 and D is 10. So the 12th term we found in one of 2 ways. Just keep going. Let's see, is that it? 1, 2, 3, 4, 5, 6. One more. Okay. That's it, 112. Or we can use the formula. Okay, so we started with 2, and the common difference here is 10. So we're going to have 2 plus 11 times 10. 2 plus 110. And that equals 112. All right, and then finally we will do our sum. And we'll do that with our typical formula. Let me just grab those. So you can still see what we were doing. So here the first term we need is 2, and the 12th term is 112. Oh, wait a minute. Uh-oh. I just realized I screwed this up. This one is not 684, it's 588. I was looking at the wrong thing. Sorry, this is actually 588. Yeah, I guess we should have been suspicious that 6 times 98, it's got to be less than 600. So yeah, sorry about that. That one was actually 588. See, the great thing about this is I can just edit it and there you go. But yes, so it was correct up to that point, and then it was actually 588. Okay, sorry about that. Now this one, on the other hand, we've got 2 plus 112 2 plus 112 means we're looking at 12 times 114 or 6 times 114. And this one actually is 684. All right, great. Now, what about, oh my God, look at these. Now we're getting into some scary territory because you can see that in this first case, the difference is clearly negative. It's -2 because it keeps going down 2 at a time. So to get the 12th term, again, we can do one of two things. See, is that 12? 1, 2, 3, 4, 5, 6, 7, 8. One more. 1, 2, 3, 4, 5, 6, 7. Okay. Or we use our trusty formula. So we started with 50, and the common difference is -2. Or 50 plus 11 times -2. 50 minus 22 is 28. Well, there you go. We did it correctly. All right, let me go grab the formulas for the sum of the first 12 terms. And let's see, what are the two terms we need? 50 and 28. Okay, and this one is 468. All right, now here's some fractions. Now, I think we've already encountered something like this before. Whenever you've got fractions like this, you're probably your best bet is to give them all a common denominator. All right, because otherwise it's going to be almost impossible to see what the common difference is. So like for here, oh, hold on 1 second. I just realized my tablet is not plugged in properly. All right, hold on. I have to eject another flash drive, so this might take a minute. Oh, sometimes it works. What do you know? All right, now we just plug this thing in. All right. Okay, so this is what I'm referring to. So what I'd like to do is convert these all into a common, or give them all a common denominator. So I think 24 looks like a promising common denominator. So for example, 1/8 could be easily written as 3/24 and 17/8 times 3/3 gives me 51/24. So now if you write it like this, it should be much more clear that, well, obviously the first term can be thought of as 3/24. The common difference now is clearly 16/24. Now, while both of these could be reduced, I would recommend that you not do that because it'll be easier to plug these into our formulas if you leave them all as 24ths. All right, so this is one time you have to resist the temptation to simplify these fractions. Normally, that's the first thing you do, but here we don't want to do that because we need to have a common denominator to make our calculations a little bit simpler. So here we have 8, 12. And by the way, in this case, I suppose we could crank them all out to the 12th, but I think this time maybe we'll just use the formula because it's going to be quite a mess. Let's do it like this: 3/24 plus 12 minus 1 times 16/24. All right, equals 3/24 plus 176/24. And finally, when you're done, the 12th term would have been 179/24. Let's see. Yes, that's right. Now, again, you could reduce this to a fraction or something. I would just leave it like that. There's no, you don't have to do it, make it any simpler than that. And then as far as the sum is concerned, of course, we'll use the same formula, but it'll be a little more complicated by the fact that we're dealing with fractions. So remember, A1, we rewrote it as 3/24. Oh, oops, sorry. We need that we don't want the parentheses just yet. Okay, so we'll have 12 times 182/24 all over 2, which is equivalent of 6 times 182/24. And if you multiply 6 times 182, you'll get 1092/24. And again, I'm sure we can reduce this. In fact, it turns out that this is actually 91/2. If you want to do that, it's fine. You can leave it like this, but if you divide the numerator and the denominator by 12, you'll discover that you've actually got 91/2. Either one of these is fine. All right. So yeah, it's a little messier, but the key to the whole thing was to find common denominators for all the terms in the sequence so that we can easily determine the common difference. And then we leave everything in the denominator. Those all 24ths to make our calculations a lot simpler. All right, now there's one more of these. Again, we have fractions, but this time the fractions are not quite as messy. There are tenths. Tenths are easy to work with. In fact, the only change we really have to make is the first one. Let's convert that into 5/10. So A1 is 5/10. And D is 4/10. Okay, so again, why don't we, I mean, we certainly could write out the 12 terms, but I'll tell you what, this time, when we're dealing with such messy expressions, why don't we just use the formula? You can still write them out if you want to double check, but let's just do it this way. It would never stop you from double checking your results, but it might be a little overkill this time. So anyway, we have A12 is 5/10 plus 12 minus 1 times 4/10. And that leaves us with 49/10. I don't think you can reduce this one. It's just 49/10. No, that's as simple as it's going to get. And then we need the sum of the first 12 terms. And so for S12, 12 times A1 is 5/10. (49/10) over 2. 12, here we'll have 54/10 over 2, which is equivalent to 6. (324 over 10), which you can reduce to 182 over 5, but either one of these is fine. Okay, so now we're switching over to geometric sequences. And so we just recall from the slides that geometric sequences mean they have a common ratio instead of a common difference. So in other words, you're multiplying each term as you go through the sequence. So here they're giving us the first term and the common ratio. And we, of course, have to put this together. So first, what is the first 5 terms in a case like this? We start out with a 12, and then we double the terms as we go along. And so, yes, this is what we were looking for, 192. Now, the 12th term, well, I'll tell you what, we could multiply these out and find the 12th term, but the numbers are going to get so big that I think it might be best if we don't do that. Let's use our formula. Now, for this set of sequences, for the geometric sequences, the formula is, of course, different. Here we have n is A1 R to the n minus 1. Okay, so let's do some plugging in. Now remember, we're looking for the 12th term. A1 is 12. R is 2. The exponent will be 12 minus 1. Okay, so if you take out your calculator, you'll see that 2 to the 11th is 2048. And so when you multiply that by 12, you get 24,576. Okay, So you see what I mean? If you kept writing it out, you would have said, oh my God, look how big these terms are getting. It would be very easy to make mistakes along the way. So probably in this case, you should stick with the formula. Although you could certainly feel free to go ahead and double check it. But now we're ready for the sum. Again, it's the sum of the first 12 terms. Now, what formula do we use here? Well, it's a little bit different. And let me get my equation editor here. All right, here we go. Sn equals the ratio of A1 times 1, not what I wanted to do. 1 minus r to the nth power over 1 minus r. And so, let's leave it like that. Let's plug in the numbers. So we've got S12 equals, now A1, as you know, was 12. And then we have, this is 2 to the 12th power. And then here we have 2. All right. So this is a little bit messier than what we're used to seeing. 2 to the 12th is, I think it's 4096. Let me confirm that. 4096, yes. So we're going to have in the numerator negative 4095 over -1. Now the -1 will just simply cause the negatives to cancel out. So what you're really doing here is you're multiplying 12 times 4095. And that will give you a sum of 49,140. All right, so that's how we do those, okay? All right, what else? Is that it? Yeah, we got the first 5 terms, the 12 terms, and the sum of the first 12. All right, perfect. All right, that's A. Now for B, what's going on here? Let's start with 8. Oh my God, this one is tripling. It's going to get huge in no time. Okay, so those are the first 5 terms. Okay, so the R is, we're still looking for the 12th term. The R this time is 3, so we only have to make that one change. 3 to the 11th is 177, 147. $2 million. Oh my God. You can see these things get huge in a hurry. Hold on a second. Oh, whoops. Wait a minute. I just realized I made a mistake. This 12 was supposed to be replaced by an 8. Ouch. Yes, that's right. I missed that. Because this is not the 12 from N. This number is actually A1, which is 8. Okay, so it was supposed to be 8 times 3 to the 11th. All right, now we're getting somewhere. 1 million, yeah, that's it. 1 million. And again, you can always double check this. Although it might be more trouble than it's worth, but just by multiplying each term by 3, you'll discover that the 12th term is in fact 1,417,176. All right, and then for this one, all right, so A1 is 8. A1 is 8. And the common ratio is 3. All right, now 3 to the 12th is 531, 441. Down here we have -2. Now 1 minus 531, 441 is simply -531, 440. So basically, all right, let me just, this is getting too long. I'll finish it on the outside here. There we go, because what you can see here that you've got a 12 and a negative in the numerator and a -2 down here. So this is equivalent to multiplying 6 times positive 531, 440, and that equals 3,188,640. I think, wait, did I screw this up? Let me try that again. Oh, you know what happened? Again, I made a typo. I did that again. Sorry, hold on. I forgot to change that 12 back to an 8. No wonder it's not looking good. Yeah, this was supposed to be an 8. All right, that's much better. And then when you divide 8, -531, 440, this is equivalent multiplying this by 4, not by 6, by 4. Okay, and so instead your answer is 2 million. That's a lot more like it. 2,125,760. Okay, so now we're good. Beautiful. All right, I think that was it for that one. A and B, that's correct. Then in part 4, which is the end of it, you can see that now, once again, you're given the actual sequence and you have to figure out the starting point and the common ratio, and then apply the same formulas. We need the 12th term and we need the sum of the first 12. So for this one, it should be clear that A1 is 4 and R is 3. All right, so let me go borrow some formulas from up here. Here's our 12th term. A12 is 4 times 3, 3 to the 12 minus 1 power. 4 times 3 to the 11th. 3 to the 11th is equal to 177, 147. And when I multiply that by 4, I should get 708, 588. Okay. So that's the 12th term. And then for the sum, I need to use our formula. Go steal that from here. All right. All right, so A1 is 4. 1 minus 3 to the 12th over 1 minus 3. Three to the 12th. Ooh, it's 531. 441. Anyway, so that all reduces to, let me just do this. 1,062,880. All right, actually I did, let me just add one more step in here. And then we have 4 times negative 531,440 over negative 2. And then, yes, and then it works out to be that number. All right, so that should do it. All right, we're good. All right, here we have A1 is 6, and you can see the common difference is clear. Sorry, the common ratio is 2 because we're just simply doubling the numbers as we go along. So once again, we're looking for the 12th term and the sum of the first 12. So let's do that. So A12 therefore equals 6 times 2 to the 12 minus 1 power. 6 times 2 to the 11th. 6 times 2048. And that gives us 12,288. All right, so now what about the sum? Let me just recycle this formula right here. What's different now is that A1 is 6 and the common ratio is 2. All right, so we plug these in. And we have 1 minus, this is 4096 over negative 1. So we'll have 6 times minus 4,095 over negative 1. And when you multiply those out, you should get, remember the negatives cancel, 24,570. All right, so that's that. Now, oh, here we go again. We've got fractions, but it turns out this time we don't have to worry about common denominators because here's what's actually happening. The first term, of course, is a half. But you know what? Every time we multiply, what do we multiply each term to get to the next one? Why, that's also 1/2. So it's pretty straightforward here, okay? Because of course, 1/4 is 1/2 times 1/2. 1/8 is 1/4 times a half. So in other words, both of these are actually 1/2. So therefore, We have to be a little careful with this. Now, by the way, since these are both 1/2s, you can simplify this a little. This is actually equal to 1/2 to the 12th power. And that in turn could be rewritten as 1 to the 12th over 2 to the 12th. Whoops, that's 4096. Okay, and then you're done. Now for the sum, ooh, this one's going to be a mess. I'll tell you what, let's do this one by hand here. Sn equals A1, 1 minus R to the N over 1 minus R. Wow. Ooh, this one is tough. All right, so you just have to be careful. A1 is 1 over 496. R is a 12, a half rather. The exponent is 12. All right, so here we go. So 1/12, as we just saw, is equal to 4096. So now, in order to evaluate what's in the parentheses, we can rewrite it as 4096 oh, wait a minute. No, what did I do? Sorry, A1 is a half. I wrote the wrong thing here. This is a half. Oh, boy, that helps. Okay, sorry, that's 1/2. Yes, that will make things so much nicer. Okay, great. I'll tell you why, because of course these halves cancel each other out. So you know what I'm going to do? Let me just rewrite this as 1 minus 1 over 4096. Okay, much better. Now, though, we do need a common denominator. Let's choose 4096. So the final result is 4095 over 4096. It's just a pinch under 1. Okay, there we go. All right, let me give you a second to recover from that one. All right, one more, and then I think, oh no, 2 more. Okay, 2 more. All right, now these are again clearly all geometric sequences. So we need the first 5, sorry, the 12th term and the sum of the first 12. All right, now let's look at this one. Now again, you can see it might look like a disaster when you first look at it. But guess what? It's not hard at all because the common ratio is simply a third. How can you tell? Well, look at them. 2/3 times a third is 2/9. And then when you multiply that by a third, it becomes 2 over 27. So the common ratio is a third. So once again, we need the 12th term. So we'll use that formula again. And in this case, this means that A12 is 2/3 times 1/3 to the 12 minus 1. Now we have to be careful with this one, but watch what we can do. 2/3, 1/3 to the 11th is equivalent to 1 over to the 11th power over 3 to the 11th. 1 to the 11th is just 1. In the denominator, since we have 3, this is actually 3 to the first power. So this can be rewritten as 3 to the 12th. And then we can rewrite that as 2 over. And of course, 3 to the 12th is, this keeps popping up over and over again for some reason. 2 over 531, 441. And that's it. Oh, man. These geometric sequences can be very, very messy, as you can see. And then finally, we need the sum of the first 12 terms. So S12 would therefore be, remember the first term was 2/3. Oh, let me write this a little cleaner. I'll just put it on the next page. Oh, you know what? Let me just double check one thing here. You know, there's a technique you can use in Word that, you know, you can split up the pages and unsplit them, but sometimes that can throw off the handwriting. So I have to make sure that I have not goofed up anything. No, it looks good. Yeah, sometimes for convenience, you see these gaps between the pages. Sometimes you can get rid of them if you want to, but you have to be careful. The handwriting can get moved around. And so it looks like that did not happen. All right, that's good. I hate it when I have to fix all that writing, but sometimes it is necessary. All right, I'm just going to sneak this down here because we need the room. All right, so S12. So remember in this problem, A1 was 2/3 and R was 1/3. All right, that's better. Okay. Now we have some simplification to do. Let's see, how can we make this as simple as possible? Well, one thing we can do is this. Just by lucky coincidence, we can cancel out these 2/3. Okay, that's a little easier. And then we have 1 minus 1 over 3 to the 12th. It means the same thing. And there's, again, that number that we keep running into, 531, 441. Well, we've seen it a lot today. 3 to the 12th is 531,441. Now, in order to consolidate these two, we have to have a common denominator. So let's make this very simple. So again, it's just a tiny bit under 1. It's just barely misses being 1. So it's going to be something like 0.999999999. And it goes on for quite a while. So that's our final result. Okay. So, wow, that was a mess. All right, one more, and then we're finally done with this. Then we can move on to the probability theory. Now, here, there's no fractions, but we do have negatives, so we have to watch it. A1 is -3, but if you notice the signs alternate, which implies that the common ratio is also negative. All right, that's the only way that the signs can alternate. So we have -3 for A1, R is -5. All right, so once again, the 12th term will be calculated as -3, -5, okay, to the 11th power, all right, so yeah, this is pretty straightforward. Just go to your calculator. -5 raised to the 11th power. Oh my God. It's -48. 48,828,125. Okay. 146 million. Wow, this is a rapidly growing sequence. 484, 375. Whoa, well, so far that's the biggest number we've seen today. And then of course for the sum, it's going to be, now the sum might surprise you. I'll tell you why. Because they're alternating between negative and positive. So you might expect a gigantic number, but in fact, it may not be that big at all. All right, let's find out. So in this case, remember that the first term was -3. And the common ratio was -5. Okay, so you just have to watch out with those negatives. So minus 5 to the 12th power is 244 million 140 625. And then, of course, in the denominator, we have 1 minus -5 is 6. So we have -3, and then we have 1 minus 244, 140, 625. That's minus 244, 140, 624. All right, when you throw that in your calculator, you end up with 122,070,312. Now, that is still a huge number, but guess what? It's actually smaller than the 12th term. Why is that? Again, because half the terms are negative and half of them are positive. So there's a lot of canceling going on here. And so that's why it's a relatively small number, at least compared to the size of the 12th term. All right, well, that one's done now. I just have to do one more thing here. This is, I think I've mentioned this many times. One of my, oh, there it is. I did insert a page number. Okay, good. The weird thing about Microsoft Word is that you don't get page numbers unless you ask for them. Why would you ever not want page numbers? You know what I mean? You'd think that they would make you turn them off if you don't want them, but what are you going to do? All right, well, guess what's next? There's one more problem set. This one involves probability theory. Okay, so let me go get it. This one I think is a little bit more straightforward. Well, it's conceptually a little bit different, but I think, well, certainly computationally, it's a lot easier. Let me quickly save it. It's just different. All right, wait a minute. Here we go. All right, and today's, of course, December 1st. It's hard to forget. Okay, here we go. We have an experiment that consists of choosing a card from a deck, and we replace the card, and then we choose another card. Now, by the way, that's a hint. Okay, so I'm going to make a note here. This is known as sampling with replacement, which guarantees that the cards that are drawn are independent of each other. Because each time we go to pick a new card, the entire deck is still intact. We put the first one back. Probably we shuffled it up, but we put it back so that you have the same number of cards each time. That's an important detail. Now, A represents both cards being red. So you can actually write that as RR, okay? So in other words, if we think of R as red and B as black, although now that I think about it, that makes it a little awkward because we named the events A and B, but all right, well, we'll see. At least one is black means two blacks, one black and red and black. So that's what they're telling us. These are the two events. The sample space, which we should have put it first, consists of 4 possible outcomes: red, 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 black, black, red, and red, red. Oh, sorry, black, black. Those are the only 4 possibilities. And one more thing, because half of the deck is red and half is black, the probability of choosing red is 1/2 or 0.5 and a black is 0.5. This implies probabilities of RR, RB, BR, and BV are each 0.25 or 0.5 squared. So in other words, what we're saying here is that this is one of those cases where all the elements in the sample space are equally likely to occur. That's an important detail. It will help us, it may help us with our calculations. Okay, now, what is the sample space of this experiment? Well, I've already put that down for you. Here it is. In fact, I've already done some of this for you. The sample points are the elements of a, let me just mention that here in case we forgot. The sample points are the elements of a set. So when they say, what are the sample points in A? All they want to know is what belongs in set A. Because remember, we define A as both cards are red. And then for B, well, we've already seen that as well. B contains RB, BR, and BB. All right, so with all that being established, the probability shouldn't be too difficult to calculate. A, now with A, there's a couple of options. So first of all, since each element in the sample space is equally likely to occur, we can compute this as the number of elements in A over the number of elements in the sample space . Three-fourths or 0.75. Or we can do this. Since A only contains the element RR, well, there you go. It must have a probability of 1/4. Now, B, based on the same logic, the probability of B can be thought of as N of B over N of S, or 3/4 or 0.75, or else you could just say, well, you know what? It's the probability of getting RB, BR, and BB, or so there's multiple ways of doing it in this case. If the elements in the sample space are not equally likely, then we can always use this approach, the second approach. Okay, but you know, in a simple case like this, all you have to do is count how many elements are in B, which remember is RB, BR, and BB, divided by the sample space size, which is 4, and we end up with 3/4 as our probability. All right, now what about these? These are the so-called compound events. These can be often solved with a rule or possibly just simply by observing what elements belong to that particular set. So here, for example, let's just remind ourselves what's in A and B. So if you notice, they have no elements in common. Okay, A and B have no elements in common. So their intersection is the empty set. And we can also say that A and B are mutually exclusive. So therefore, this implies that the probability of A and B is 0. All right, so they have nothing in common. Therefore, the probability of this happening, getting your card as either 2 R's or RB, BR, and BB, can't happen. All right, it's got to be one or the other. So that probability is simply 0. And you could also say, if you want to take this one step further, A intersect B is an impossible event. All right, now, what about A union B? Now, that's a different story altogether. With the union, you're simply combining the two sets. All right, so here's what you can do. You'll note here that the union is simply the sum or the combination of all of these elements and if you notice now all of a sudden there are 4 elements in this set, all of which are equally likely. So you can do this in one of 2 ways. Actually, there's a third way we can do this. Let me show you in a second. We can do this approach. Basically, we're counting how many elements are in the union divided by the number of elements in the sample space, 4/4, which is 1, or we can just calculate the individual probabilities of the elements of that union. And that, of course, turns out to be, as we've seen, a quarter plus a quarter plus a quarter plus a quarter. Any way you look at it, it's 1. And also, we could use the addition rule. Whenever there's a union, we can always apply the addition rule. So there's a third way of doing this. Wow, so we have so many options here. Let me just see if I can sneak it down here. So you might recall that the addition rule is this. And those numbers we've already seen. All right, remember before we determined that A has a probability of a quarter, B is 3/4, the intersection is empty, so we end up with 1. So any way you look at it, this is equal to 1. There you go, interesting. All right. So now what about these? The complements, they can be easily determined with the complement rule. All right, so you might recall that the complement rule tells us that the probability of a complement is nothing but 1 minus the probability of A, 1 minus a quarter, or 3/4, or 0.75. Same thing with B. This is a very simple calculation. So this time we're subtracting 3/4, a quarter, or 0.25. Oh, hold on. All right, so now this is the conditional probability of A given B. Now, this one requires a specific formula. So this is the definition of this probability. This is the conditional probability of A given B. And it is defined as the probability of A and B, or A intersect B, divided by the probability of B. Now, it turns out we've already discovered that A and B is empty. So this is just zero. Well, that simplifies things a lot, that's for sure. And then B given A, well, that formula is similar, but note that the key difference is that the denominator is different. The probability that goes in the denominator is this one. So here we have 0 over 1/4, which is again 0. All right, so that's how that's done. Now, here's some conceptual questions. Are A and B mutually exclusive? Why or why not? All right, well, let's remind ourselves what that means. A and B are mutually exclusive if they have no elements in common. All right, so you recall again, A and B, let's remind ourselves how they were defined. And you can see they have no elements in common. So since A and B have no elements in common, they are mutually exclusive. Now, this can also be demonstrated in two equivalent ways. First, we've already determined that the intersection is empty. And that the probability of their intersection is 0. These all mean the same thing. They all demonstrate that A and B are in fact mutually exclusive. All right, and then this one, independence. Now, independence requires two things to be true. Or I guess what I should say is independence implies that two things are true. The probability of A given B must equal A, just plain A. And the reverse must also be true in the sense that the probability of B given A must equal the probability of B. Now here, the probability of A given B is 0, while the probability of A is 1/4. So they are not equal. Now, once we determine this, we don't have to demonstrate the other version or the other condition. But I'm going to show it to you anyway. All right, so in other words, both conditions fail to hold. But as long as at least one of them fails, we can conclude, since it is not the case that both conditions hold, we conclude that A and B are not independent. All right, so in other words, both of them have to be true. Here, both of them were false. Okay, so therefore, our conclusion is that A and B are not independent. All right, now. Here we go. Our favorite table, a joint probability table. Now, here what we see are the different style or flavors of sodas, the different brands, I should say, and whether they're regular or diet. Now, much of the information we need can be read directly off the table, but in some cases, we still need formulas. But it's a very straightforward process. So, for example, C intersect R. What does that even mean? Well, that tells me that the soda that I've chosen from this collection is regular Coke. Okay, R is regular, D is diet, C is Coke, P is Dr. Pepper, S is Sprite. So all I have to do is look for the intersection of R and C, and it's 0.32. Regular Coke represents 32% of these sodas. Now, P and D is Diet Dr. Pepper, which is right here. So these are easy. They're very easy. And then this one is S&R is regular Sprite. Wow, that couldn't be much simpler. Okay, now S means just Sprite, regardless of whether it's regular or diet. So this is 0.26. And similarly, R means regular, all the regular. It doesn't matter whether it's Coke or Pepsi or whatever. I'm sorry, Coke or Dr. Pepper or Sprite. That adds up to 0.61. Now, here we start to need the rules. Okay, for example, here we've got a complement. RC, our complement is obtained by, actually, let me do one thing here. By using the rule, 1 minus PR, 1 minus 0.61 or 0.39. So that's all you have to do with that one. Now, here again, we need rules. Now, C or P. Now, I just want to point out the columns in this table are mutually exclusive of each other. In other words, the same soda can't be both Coke and Dr. Pepper, for example. And also the rows are independent, or they're mutually exclusive. For example, the same soda can't be both regular and diet. Therefore, we can use the simplified addition rule to calculate this union. All right, so in other words, we're going to use the simplified because it's understood that Coke and Dr. Pepper are mutually exclusive of each other. So therefore, all we have to do is C, probability C, plus the probability of P. C has a total probability of 0.48. P is 0.26. So the probability of picking either Coke or Dr. Pepper is 0.74. Okay. So you don't have to bother subtracting the intersection because there isn't one. All right. And now the same logic holds for this next one. All I have to do is add up the probability of Dr. Pepper and the probability of Sprite, which is 0.26. Oh, just by coincidence, they're both 0.26 for a total of 0.52. Okay, now next we have some conditional probabilities. So for these, we have a special formula. So for example, here, this is the probability of R and C over the probability of C. This is how the conditional probability is defined. R and C is regular Coke, which we've already seen is 0.32. Coke by itself is 0.48. That's the sum of that column. And 0.32 over, this is actually 2/3. We can rewrite this as, let's say, 667. All right. And the next two will be done in exactly the same way. In other words, here I'll have D and S over S. D and S means Diet Sprite, 0.11. S is just Sprite, 0.26. And this ratio is approximately equal to 0.423. Beautiful. And so finally, there's one more conditional probability here. And that would be P given D. And we will see that that's equal to the probability of Dr. Pepper and, in other words, Diet Dr. Pepper over Diet. So P and D, Diet Dr. Pepper, is 0.12. Diet, all the diet sodas are 0.39. And that ratio is about 0.308. All right, so these tables are awfully helpful in coming up with all these fairly complicated probabilities. We don't know any of the details behind the scenes as to where these numbers come from, but we do know that this is our probability distribution. And with that information, we can calculate any probabilities that we need. All right, so now all that's left is this one brief section on combinatorics. And you might remember, let me just briefly review with you, an arrangement is an ordering of a set of objects. For example, if a bookshelf has room for 3 books, then each order in which the books are placed on the shelf is an arrangement. A combination is a selection of objects from a group where the order of selection does not matter. Okay, and finally, a permutation is a selection of objects from a group where the order of selection does matter. All right, and then we had formulas for all 3 of them, and we'll review those as we go along. But the key here, with these types of problems is that we have to know whether it's an arrangement, whether it's a combination, or whether it's a permutation. Once we have that in place, we can just simply apply the appropriate formula. All right, so we start with an author that has written 8 books and wants to display them on a shelf in his office. How many different arrangements are possible? Well, it says the word arrangement. So you'll recall, hold on. All right, well, that took up a lot of space. I'm just going to copy this down here. The number of ways, or the number of arrangements of n objects that can be formed is n factorial. So with 8 books, the number of arrangements is 8 factorial, which, as you know, equals 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And in order to avoid multiplying them all together, you can go to your calculator and discover that it's 40,320. Or you could just do it yourself. But, you know, this is kind of messy. I think you're probably better off letting the calculator take care of that for you. All right, so that one was easy. Now, what about B? In a standard game of 3-card poker, which maybe you played, maybe you haven't, you may not have even known there was such a game. Yes, there is. It's got to be challenging because we're so used to the values of the hands with 5 cards. 3 is a little tricky, but what's happening here is that everybody gets dealt 3 cards. And because the order in which you receive your cards does not affect the value of the hands, these must be combinations. Each hand is a combination because 3 cards are chosen from a deck of 52 cards in such a way that the order of selection does not matter, does not affect the value of your hand. Now, how do we calculate combinations? The formula is this. And we sometimes see, by the way, this represents the number of combinations where n is the number of objects R is the number of objects chosen. And so it can be rewritten as and in this case, n is 52 and R is 3 because we're picking 3 cards from a 52 card deck. So you're reducing this to 52 factorial over 52 minus 3 factorial times 3 factorial, or 52 factorial over 49 factorial times 3 factorial. Now, you can throw this into your calculator, but let me show you a way of simplifying a little bit. I just want to point out that 52 factorial can be simplified by noting that it contains 49 factorial. In other words, it can be rewritten as 52, 51, 50, and 49 factorial. Why does that help? Because now all of a sudden, we don't have to deal with these gigantic numbers anymore because we have some cancellation. Oh, that makes it so much easier. And 3 factorial is just 6, or 3 times 2 times 1. All right. So when you multiply this out, what do you get? Well, let's see. 52 times 51 times 50 is a huge number. 132,600, but it's nowhere near as big as 52 factorial. So when all the work is done, you'll see that this works out to be 22,100. Okay. Now, if you have the right calculators, some of the more advanced calculators already have this NCR button built into them, so you can do it that way. But if not, you can use this formula. Okay. But either way, the answer is 22,100. All right. So now part C says the following. There's a prize. Well, first there's a class of 10 students. All right. Looks like prizes are going to be available to us. There's 10 students in the class. They're playing an investment game in which there's a prize of $100 for finishing first, a prize of 50 for finishing second, and 25 for finishing third. How many ways can the prizes be distributed in this class? So what we're seeing here is that each distribution of the prizes is a permutation because the order of selection matters. Okay, why do I mean? Well, because imagine that, for example, that the prizes go to, or let's put it this way, that student number 7 wins the first prize. Student 4 wins the second prize. And student 8 wins the third prize. This can be expressed as 7, 4, 8. If instead student 8 wins first prize, student 7 wins second prize, and student 4 wins third prize, this is expressed as 8, 7, 4. Now, since these outcomes are very different, in other words, the distribution of cash to the students in each case, then 7, 4, 8 is a different permutation than 8, 7, 4, in spite of the fact that they are the same numbers. In other words, this is a long-winded way of saying the order matters in this case. So since the order matters, each distribution of prizes is a permutation. And that's going to affect the way we calculate it. So therefore, the formula we need is NPR, and that's equal to n factorial over n minus r factorial. And in our case, since there's 10 students, n is 10, and there's 3 prizes, so r is 3. So the number of ways we can distribute the prizes is therefore Okay, well, that looks pretty straightforward. And again, if you do not want to deal with the enormous numbers, what you can do is rewrite this as 10 times 9 times 8 times 7 factorial. Those cancel out, and look what that turns out to be 720, which is not a gigantic number. Okay, you don't have to do it that way. You can just calculate the factorials directly. These factorials aren't really that huge. You might be okay with that. Let me put that over here somewhere. Ten factorial is 3,628,800. And 7 factorial is 5040. And if you plug that into your calculator, you'll see that that ratio is equal to what we're looking for, which is 720. Either way, you'll get the same result. There are 720 ways of distributing the prizes to these students with the order matters. All right, well, it looks like we're done with our second problem set here. So we've now completely covered chapter 11. And now all that remains is to finish up 12. And like I said before, next week, we will have to do two things. We'll have to do the chapter 12 problem set and the sample final, which only covers 11 and 12. So if we need to finish 12 next week, we can do that too, but we'll have to do both the sample final and the chapter 12 problem set next week because that's our last meeting. So for the rest of today, after the break, we're going to just carry on with chapter 12. Okay, I'll quickly remind you what we've been doing and then show you where we're going. All right, so let's put this away and let's go have our break, which I'm sure we desperately need by now. And when we get back, we'll pick it up with chapter 12. All right.
Hey, can I ask you a
In a few
question real quick?
minutes.
Did you by any chance get to grade my midterm yet? Hey, Professor, I got a question. Can you hear me?
All right, so I think
Wait,
it's time to go
can I-
back and revisit what we were doing last time.
Wait.
Now, well, let's go back to the beginning. This is chapter 12. Now, let's hold on a second. Let me just go get the others.
Can I ask you a
Chapter
question?
12 is actually broken up into multiple parts. And I've got one open. Here's 2, and here's 3. And we may not have time to do all of these parts. That's one of the reasons why I split it up this way. And if not, well, you can read the slides and it'll be for your own benefit, but it's not necessarily the case that all of these will wind up on the final exam. So I just want to mention that right now. The third and final one actually is an application from economics, which again, we may or may not have time for this. It's kind of an interesting look at how these concepts can be used in practice, but if we run out of time, certainly that we might not have time to do that. The second one, oh, that's all right. The second one involves, okay, well, these are applications as well. But this is getting a little bit more involved. Again, it's possible that we may not have time for this either. Because like I said, if you're going to end up in Calculus 1 anyway, you'll see all these ideas again, and you can use these slides for review. But the only one that we definitely need to do is part 1. It's a fairly long section, but what it does is it introduces some very important ideas that you'll definitely need in Calc 1. So we briefly discussed limits. What I'd like to do is take a look now at the derivative. Now, the derivative is really one of the most important ideas in all of calculus. What exactly is it? All right, well, think of it as a rate of change. In fact, let me just show you a quick graph of that. Imagine we had some kind of a function. And let's say that this function represents profits. All right, so this is our profit function, and let's say it's a parabola. No, sorry, it'd be the other way around. Let's keep it simple. This is a parabola, and it represents a corporation's profits. So Y would be profits, and X would be units sold of whatever good that they sell. Now, you see what's happening here is that they break even. Let's say this is 10 and this is 100. That means the company breaks even if they sell either 10 units of the product or 100. In between, the profits continue to rise, but there's a limit to how far they can go. And let's say that that limit is 50. When we reach 50 units, our profits are maximized at, let's say, I don't know, $1 million. So this graph is showing us that whatever we produce, we can figure out what our profits are, but ideally we would like to produce 50 units of this good, and then our profits will be $1 million. So why is this happening? Well, what's happening is that a lot of this reflects the cost of producing this good. When we get past 50, for whatever reason, the cost of producing the good starts to rise fairly significantly, and so therefore our profits start to fall off. So how does this lead us up to the idea of a slope, or derivative rather? The derivative could be thought of as the slope of this curve at any given point. Hold on one second. And that can be expressed in terms of geometry as the slope of a tangent line to that function. So here, this tangent line has a negative slope. And over here, it has a positive slope. At the point of maximum profit, the slope is 0. So the slope being positive, so when we're at 10, let's say this represents 15 units of output. The fact that the slope is positive means that we can improve our profits if we continue to produce more units. And that will continue until the slope equals 0. When the slope is 0, if we go past that by even 1 unit, let's say to 51, our profits start to decline and the slope of this curve becomes negative. So we can tell that this is the ideal spot to be producing because, of course, the curve itself shows it to us. But the important detail here is that the slope of these tangent lines goes from positive to 0 to negative. And so that means up here on the top, this is where we want to produce. The derivative is basically the formula or equation of these tangent lines. And by having an equation like that, it's easier to tell where in this curve the slopes are increasing, where it's decreasing, and where it reaches its maximum value. So think of the derivative as simply the equation of the slope of a line or tangent line to a function. Now, this is a fairly simple case. The parabola, this is a function like, let's say, y equals negative 2x squared plus 4x minus 5 or something like that. It's a simple case, so the derivatives are easy to calculate. But for other types of functions, the derivatives can get very, very messy. So what we're going to learn here is some techniques for calculating derivatives, but keep in mind, ultimately what they're for is to help us figure out where in a function we have the maximum value or do we have the minimum value if there is one, and where's the function increasing and where's it decreasing. So we're going to introduce the concept of the derivative, and we're going to do that by introducing a series of rules. Okay, so we're not going to go through the formal definition because it's very complicated. Instead, we're going to show you several rules that you can use to calculate derivatives. And at first, they may seem very scary and intimidating, but after you've done a few of these, you'll realize they're really not that difficult, especially when they're applied to polynomials. For very scary formulas that involve tangents and arctangents and things like that, the rules start to become very complicated. But we're going to stick with some very basic cases. Like I said, most of these involve polynomials. And so we're going to learn the rules, and then we're going to get some practice so that you have some sense of what derivatives are all about. So we'll start out with the so-called constant function rule. So now let's say f of x equals k. Now, k could be anything. Like it says here, 7. What does that look like on the xy coordinate system? It's a vertical line. And so remember, the slope of a line or slope of any function is delta y over delta x. And so you'll see that here the slope is actually infinity or undefined because the x never changes. So the derivative of a constant like this is defined to be 0. So whenever you run into a constant, the derivative is simply equal to 0. And because there's no change in the function. And so therefore, the derivative is 0. All right, well, that's an easy one. Now, what about a straight line? What if you have something like this? Y equals 2x plus 7. Well, then the derivative of this function, which, oh, by the way, I almost forgot to mention, when we have a function like this, the way we represent the first derivative is f prime of x. We call it the first derivative because we can actually define higher order derivatives. So we'll call that the first derivative. And keep in mind, it represents the change in y due to a given change in x. Or in terms of geometry, it could be thought of as the slope of a tangent line to that function. Now here, the tangent line actually coincides with the line. It's a straight line. So the slope is defined as 2. So the first derivative of this function equals the slope. Okay, so m is being used to represent the slope. All right, so let's recap this a little bit. Or here's an example. What if our function is y equals 3x plus 7? All right, well, we have a straight line. And we already know that when we have a linear function like this, the first derivative is just 3, because 3 is the slope of this line. Okay, so those first two cases are very simple. If we have a constant, the derivative is 0. If we have a straight line, then the derivative is equal to the slope. So those are easy, very easy, and we will run into them quite often. Okay. The next one's a little bit trickier, but once you get used to it, you'll see that it's really not terribly complicated. So, all right, so we have, again, just one more quick review here. The derivative f prime of x of a constant equals 0. The derivative f prime of x of a straight line equals the slope of the line, m. And that's all you have to remember for those two cases. But what if we start looking at higher order polynomials? Like, let's say we have a quadratic equation, which is represented by a parabola, or a cubic equation, or something like that. We have to have a rule that applies that enables us to determine what to do in those cases, because it's a little bit more complicated. So we're going to introduce the so-called power rule. So with the power rule, we're assuming that we have a term where we have a constant. And of course, x is the variable and n is the exponent. So it could be something like this. Let's say it's 3x to the 4th power. What we want to know is how to calculate the derivative. Well, we're going to use this power function rule, which is very straightforward. It just takes a little getting used to. So remember, f of x was defined as kx to the n power. The derivative is written as nkx to the n minus 1 power. So yeah, this one we're going to need to do a lot of practicing with, just to get the hang of it. Once you see how this works, you'll realize pretty quickly it's not terribly complicated. It just needs a little practice. All right, so let's look at our first example. All right, nkx to the n minus 1. Let me copy that because we'll need it again. Just a reminder. So here we go. Oh, here it is. So if our original function is, let's say, 3x to the 4th. All right, let me put that back in here. That tells me, and by the way, in general, remember, we're writing this as kx to the n power. So in this case, k is 3, n is 4. So if you look at this function, n is 4, the k is here, that's 3, and then the exponent becomes n minus 1. So when you plug all those in, you see that ultimately the derivative is 12x cubed. So for f of x equals 3x to the 4th, f prime of x, the derivative, is 12x to the 3rd power. Think of that as the slope of this function. The actual value of that slope depends on the value of x. But once we know x, we can easily determine the value of this derivative. So it's a formula that tells us how to figure out the derivative at any point on this function. All right, so let's try another one. How about this one? Six x to the minus 3 power. All right, let me write that in here. And because the general expression is kx to the n, in our case, k is 6 and n is negative 3. So here's our formula for the first derivative. N is negative 3, k is 6, and the exponent is n minus 1, which in this case is minus 3 minus 1. So that gives me a final result of minus 18x to the minus 4. And they're all exactly the same, but let's create some new ones so that you can get some more practice. All right, so far, it's just a question of plugging the numbers in and evaluating them. Okay, the actual algebra is not that difficult. It's just that you have to recognize what you're doing. All right, let me make up a completely new example. All right, so let's say that our function is f of x is 5x to the 7th power. And remember, the general rule is this. All right, so we have f of x is 5x to the 7th. The general expression is kx to the n. Okay, k is a constant, n is the exponent. And then the derivative is defined as nkx to the n minus 1. So in this case, k is 5 and n is 7. So that implies that f prime of x is 7 times 5 times x to the 7 minus 1 power, or 35x to the 6th. Wow, and that's it. All right, so while we're at it, let's do another one. All right, so in this case, k is negative 2 and n is 3, because remember, this is the form k x to the n, and the derivative is nkx to the n minus 1. So therefore, that derivative must be 3 minus 2 x to the 3 minus 1, or negative 6x squared. Okay, so after a while, like I said, if you do enough of these, you'll start to think, this isn't that hard. And it really isn't. It's just takes a little getting used to. All right. So I think we need to do a few more of these to really get the hang of it. All right, let me leave it there for a second. So yes, so and you notice in each of these cases, what we actually have here is a polynomial. If we have something different, then there are different rules that we would have to use. But for polynomials, we can always use the power rule. All right, let's try another one. Remember, the original expression was kx to the n, and the derivative is nkx to the n minus 1. All right, so we're going to apply the power rule and come up with the derivative. Okay, so let's do that right now. So therefore, f prime of x equals -4 times 9 times x to the minus 4 minus 1, or minus 36x to the minus 5. Okay, so you're starting to get used to it now, I bet. So let's see. All right. Now, you don't have to keep rewriting the definitions if you don't want to, but this way, when you see these over and over again, eventually they'll start to stick in your memory. That's how it works. That's right. Your memory needs a lot of reinforcement. So therefore, the derivative here must be -7. Oh, sorry, -8 -7 x to the minus 8 minus 1 power. And you notice the two negatives cancel each other out. So we actually wind up with 56x to the minus 9. All right. Well, I think so far we're getting pretty comfortable with this now. So I'm going to show you a slightly more complicated case. So let me give you a minute to catch up. Then I'm going to show you, when I say slightly, I mean slightly more complicated. Okay, so what do I mean by that? Let's try this. So let's say our function is this. Oh, what happened? We have two terms. So here's what you have to do. We apply the power rule to both terms. Okay, and then we add them because it's 3x squared plus 2x. Now, I do want to show you. Now, let's start with 3x squared. And again, think of this as kx to the n f prime of x n kx n minus 1. And of course, clearly this is k and this is n. So therefore, the derivative of the first term is 2, 3, x to the 2 minus 1, or 6x to the 1, or 6x. Well, what about the second term? So remember, we've got 2 of these. If f of x equals 2x, I would like to point out here, though, this is an important detail. This is the same as 2x to the 1 power. So when we write these out as kx to the n, k in this case is 2, but n is 1. So when you write out the derivative, you'll have 1 times 2 times x to the 1 minus 1. This one is 2 because x to the 0 power is just 1. So in other words, the derivatives are 6x for the first term and 2 for the second term. So finally, when we're done, we end up with 6x plus 2 for the entire expression. See, so in other words, when you have a combination of these, you're going to wind up with a sum. You also could end up with a negative or a difference. All right, now we're going to do this a little more formally in the next section. What do we do with sums and differences? Now, what we're going to do is change the way we express this slightly. We're going to do this. Imagine I have a function which is itself a function of 2 other terms, which are both functions of x. I can think of this as f of x equals g of x, another function of x, and h of x, which is another function of x. The derivative then is the sum of the individual derivatives. So the case we just looked at, which was 3x squared plus 2x, we could call this first term actually g of x, which is probably more proper. And h of x is this 2x. And we use the power rule to determine that g prime of x was 6x and h prime of x is 2. And so therefore, according to this down here, the final result is 6x plus 2. So we've just figured out a derivative by adding up the derivatives of the individual terms in our original equation. And I'm sure that intuitively this makes perfect sense. I mean, all we did was apply the power rule to both terms and add them up. Now, what about differences? Does this work for them too? Yes, it does. Okay. So let me show you how that would look. Yeah, you just change the sum to a difference. All right, so now in the next example, we'll see something very much like this. And let me just remind you once again how this works. So remember, for any polynomial that looks like this, the derivative, according to the power rule, is nkx to the n minus 1. So here we have a sum. We're going to call this first one g of x and h of x. So why don't we do this? Just because I think we're getting some good practice with this, why don't you figure out the value of g prime of x and then the value of h prime of x, and let's see how you did. And of course, at the end, we're going to add them up. All right, so based on what you're seeing up here, and by the way, the letters don't matter. I mean, it says here f of x equals kx to the n, f prime of x equals nk x to the n minus 1. That implies that the same thing holds for g and h and any other letters that we choose to use. Okay, and the same thing for h. All right, so what would you get for g prime of x? Now remember, g of x, think of this as k x to the n. K is the 3, n is the 2. So since this is nk x to the n minus 1, that is 2, 3, x to the 2 minus 1, 6x to the 1, or just 6x. For h prime of x, we have nk x to the n minus 1. Here, if you notice, x cubed can be written as 1 times x cubed. So the k is actually 1, the n is 3. So we can write 3, 1, x to the 3 minus 1 power, 3x squared. So the final answer is simply 6x plus 3x squared. All I did was add them up. So you just have to be careful. You know, like I said, sometimes with some of these expressions, if there's no coefficient, that means that it's 1. And if there is no exponent, that's also an implicit 1 there. Now, and you'll see as you go through the slides, that's exactly what we got. 6x plus 3x squared. All right, maybe we should do a few more of these. Because what's coming up next is just a little bit messier. So let's just say that this is our original f of x. Think of this as g of x, and this is h of x. Oops. So we know that f prime of x is the sum of these two derivatives. So our job is to figure out g prime of x and h prime of x. So we can think of this as usual, general case, k x to the n and g prime of x is n k x to the n minus 1, which in this now here, k is -4, n is 2. So g prime of x is 2, -4, x to the 2 minus 1, or -8x to the first, or -8x. What about g or h of x? So here we have k is 5, n is 3. So we'll have 3 times 5 times x to the 3 minus 1, which is 15x squared. And then finally, f prime of x is -8x plus 15x squared. because we calculated each derivative separately and we added them up. We have g prime of x, we have h prime of x, we add them up, and we end up with f prime of x. Okay, and each derivative itself was calculated with the power rule. Now, I want to show you a twist on this. Suppose that we had something slightly different. This time, f of x is minus 4x squared plus 5x cubed plus 8. Well, remember, the derivative of a constant is just 0. So f prime of x would equal g prime of x plus h prime of x plus 0, because the derivative of 8 is just 0. Now, we just got through showing that g prime of x is negative 8x, and h prime of x is 15x squared, 0. So we end up with the same exact result. Okay, I just wanted to throw that in there. I also want to mention that we can have as many terms as we want. Let's just say that we had this case. Imagine we have this. Let's have a third function called I. Well, then f prime of x would simply be g prime of x plus h prime of x plus I prime of x. And if it was a difference, same thing. Oh, sorry, trying to make them negative, sorry. All right, negative and negative. That implies that f prime of x would be g prime of x minus h prime of x minus I prime of x. So in principle, you can have as many functions on the right-hand side as you want. You're still going to always take each individual derivative and add them up. Or if there are differences, then you subtract. All right, now let's just see how good you're getting at this. Let me throw a new one up there and I'm going to leave it up to you to take care of it right now. All right, so just as a quick refresher, if f of x is kx to the n, f prime of x is n k x to the n minus 1. All right, so what you're going to have to do here is calculate 3 derivatives and add them up. Well, actually, no, you're not even adding them up. You're subtracting the second one, but you're combining 3 different derivatives to come up with f prime of x, using, in each case, the power rule. All right, why don't I give you a minute and see what you can come up with. All right, let's see how you did. So for the first one, this will be g of x, h of x, and I of x. So remember, this is supposed to take the form kx to the n. So therefore, in this case, k is 3, n is 5. So g prime of x is nkx to the n minus 1, or 5 times 3 times x to the 5 minus 1, or 15x to the 4th. Then we do the same thing for h of x, negative 7x squared. So therefore, k is negative 7, n is 2, and h prime of x is therefore n k x to the n minus 1, 2 negative 7 x to the 2 minus 1, 14x. And then the last one, I of x, is 9x. Now, this is an interesting case because remember, there's an implicit 1 here. So therefore, k is 9, but n is actually 1. And so we'll have n kx to the n minus 1, 1 times 9 times x to the 1 minus 1, which is 9x to the 0, or just 9. So finally, when all the dust settles, we add them up, g prime of x. We can actually write it as g, h, and I with the understanding that h is negative. All right, so when we bring them together, we get 15x to the 4th plus 14x plus 9, and that is the final answer. Okay, so that's, wow, that was a bit of a mess. But all we did was apply the power rule 3 times. Oh, wait, sorry, I just realized I made a mistake. This one over here was negative, my fault. I forgot the negative sign for h prime of x. That should be negative. And so down here, that should be negative. Okay. So now I think it's time to introduce, there's 2 more rules that I'd like you to see. And that's probably going to have to be as far as, well, all right. Well, all right, we'll see how that goes. We'll play it by ear. We'll take it as far as we can. All right, because remember, next week we have to do the problem set and the sample final, but we also need to wrap up this material. So I don't want to get too deeply into this. That might be overkill. I just really wanted you to have a basic understanding of how derivatives work. We don't have to do every single example or every single technique, but there are certain ones you do have to be familiar with. So the next one is a bit messier. This is the so-called product rule. And you'll see right away what I mean. Instead of adding g of x and h of x, we're actually multiplying them. And you can see that really complicates things quite a bit. Oh no, look at that. So we know how to calculate h prime and g prime, but we have to remember to plug them into this far more complicated formula rather than simply adding them and subtracting them. All right, so let's take a look at a quick example of this. Let's say, all right, here we go. Now this will be our g of x, and this is our h of x. And remember, we know how to calculate G prime and H prime based on the power rule. Okay, so let's start with G of X. So remember, this is written as K X to the N, which implies that G prime of X is N K X to the N minus 1. And in turn, we know that K is 3 and N is 2. So when we come down here and we plug in the numbers, 2 times 3, x to the 2 minus 1, this is actually 6x to the 1, but that's the same thing as 6x. What about h prime of x? Ooh, all right, well, let's look at it. And once again, this is based on the premise that this is a polynomial function, which is written in the form kx to the n, which implies in turn that the derivative is nk x to the n minus 1. And here we can see that k is 2 and n is 3. And so we have h prime of x is nk x to the n minus 1. 3 times 2 times x to the 3 minus 1, 6x squared. Now, if this had been an addition problem, we would just add the two functions together, g prime of x and h prime of x, but unfortunately, this was a multiplication problem. So we have one fairly complicated step ahead of us. So here's how it works. So just remember, g prime of x was 6x. Let me just write that back up here. H prime of x turned out to be 6x squared. The original g of x was 3x squared. And the original h of x was 2x cubed. So now we're substituting these into this formula. So here we go. Here's g of x. Here's h prime of x. Here's h of x. And here's g prime of x. Now, once you've done that, now you notice here, these consolidate very nicely. In other words, this first one, when you multiply this out, it's 18x to the 4th. And in the second case, it's 12x to the 4th. And then you could just add them up. This is an unusually simple case. It doesn't usually work this well. Okay. No, very rarely. Okay. So this is the product rule. Now, let me just quickly show you. We're not going to have time to do this right now, but there is also a quotient rule, and it's even messier than this. So we'll have to save this for next time. We want to do this from scratch. And when the quotient rule is done, there's really only one more rule that we really need to be familiar with. And I think we may have to stop the new material right about here. There's so much more, but we really only need the basics. So we'll learn 2 more rules, and then that will have to be it for the new material. So I better double check then the chapter 12 problem set. I may have included things that we aren't going to do. Let me do that before you start working on it. And the same thing with the sample final. I think that I may have to tone it down a little bit because I may have included things that we haven't actually gotten to. So once I corrected them, I'll post them, and then you can work on those for next time. Okay. Because I think this is about as far as we can realistically go with this material. Like I said, I mean, if you need it, you'll probably take Calc 1 anyway, and you'll be doing a lot of this. But for now, at least you're getting an introduction to what's going on in Calc 1. All right, so let me just show you, without us doing any examples just yet, what the so-called quotient rule looks like. If you have a ratio instead of a product or a sum or a difference, then we have a formula for that too, which is going to look scary when you see it, and it is. But once we've done it a few times, you'll start to realize it's not that bad. Okay, well, here it is. And you can see why we don't want to do any more of these right now. It's a bit of a mess. But again, as long as you have the formula in front of you, all you're doing is calculating the derivatives of G and H and plugging them in, and you find your ultimate result. Okay, so let's stop right here. I'm going to go right now and look at Moodle and double check that chapter 12 problem set, because I suspect that I may have to trim it down a bit. And then I'll also post the sample final very soon, probably tonight or tomorrow. And in the meantime, what you should probably do is just review the solutions to the chapter 11 problem sets and read through the slides for chapter 12 to get ready for next week. And then, of course, work on the chapter 12 problem set and the sample final. Because unfortunately, next week is it. We're all done. That's it. There's no time to do anything else. Although I must say, we got an awful lot done this semester. This was pretty intense, and we covered an awful lot of material. So you should be proud of yourselves for absorbing so much math in one semester. It really, this was quite a class. It was quite a challenging class. And so I hope you'll, directly benefit from this in your future classes, or at least in whatever you do, for a living. But if not, you certainly have brought yourself to a level of math that very few people ever reach. If you walk around and just meet random people on the street, you won't find a whole lot of people who have more math background than this. They're just not out there. Okay, so you've really pushed yourself to a pretty high level in math. And that's something definitely to be proud of. So anyway, so if there's no last minute questions, we'll stop right here. And like I said, I'll update the chapter 12 problem set as well as the sample final. And I'll also post the solutions to the chapter 11 problem sets. All right. So I guess I'll see you. Oh, I got one right here. Oh, you're welcome. So I'll see you all next week then.
Yo, have a good weekend.
Fernando.
Professor, so midterm 2 is still due by this Friday, right? Midnight, correct? Professor. Can you hear me? Professor, can you hear me?
Yes. Yes, I can hear you. Are you not hearing me? Oh, no, I'm not hearing you. No, that's what the problem is. No, I can't hear anything. Oh, what happened?
Can
You know
hear me
what? Somehow I accidentally turned. What the hell's going on here?
Can you
All
hear me
right,
now?
we're good now.
You can hear me now?
Yes.
Okay, I was just only asking that midterm 2 is still on for Friday, right? The deadline? Midnight.
Yes. Yes, I forgot about that. Thanks.
Just wanted to confirm that. Thank you.
Okay. All right.
All right, thank you for class. I'll see you on Friday.
Yeah, then.
All right, take care.
All right, bye.
Professor,
Yes.
I was wondering about my midterm. I sent you an email about that.
Oh, yeah. The ones that arrived later, I couldn't find them. I haven't done them yet. I usually save that for the last, I usually just sit down and do them all in one shot. I haven't quite finished all the ones that either were late or somehow they never got delivered to my inbox. I'm saving those, and I'll probably work on those over the weekend.
Sure. Oh, but you're gonna like post them, okay?
Oh, yeah, the numbers will be put into Moodle.
Oh, okay, okay, that's good. Thank you.
All right, okay, see you later. Bye.